about eigenfunctions and eigenvalues. Now, generally in quantum mechanics, if you have an operator, let's say a cap, acting on a function phi, and it gives back a constant a, and that same function phi, this kind of equation where an operator a cap is acting on a particular wave function phi and gives back a constant, this is operator and this is wave function. Then the operator is acting on the wave function and gives back a constant. A is a constant which can be a real number. It can be a real number like 1, 2, 3, etc. So, and then it gives back the same wave function, the same wave function. This kind of equation is known as eigenvalue equation. And then, like we said, this is the operator acting on a wave function, giving a constant and giving back the wave function. Now, this wave function in this eigenvalue equation is called an eigenfunction. It's called an eigenfunction. So the operator is acting on an eigenfunction to give back, and this constant a is called an eigenvalue. It's called an eigenvalue. Then again, the wave function is called an eigenfunction. So in summary, we can say that this a cap is the operator acting on an eigenfunction. The wave function is called eigenfunction, and then it's giving back a constant which is known as eigenvalue, and the same wave function, eigenfunction. I think that is clear. Okay, an example of an eigenvalue equation is Hamiltonian, the Hamiltonian equation. If we have the Hamiltonian operator acting on a wave function psi, then it gives back energy E and the same wave function psi. And this is a familiar equation known as the Shrodinger equation. Shrodinger equation. So here we can say that this Hamiltonian operator is the operator actually, is the operator. Then this wave function is the eigenfunction. This energy is the eigenvalue because it is a real number. Maybe it can be something like, let's say 200 joules or maybe 0.5 joules, something like that. So it's a real number, it's an eigenvalue. And then this wave function again is an eigenfunction. So the Schrodinger equation is an example of eigenvalue equation. Now let's consider this example. Show that e raised power ax is an eigenfunction of d dx. How do we prove that e raised power ax is an eigenfunction of d dx? Now here the operator, our operator a cap, is d dx. The function psi is e raised power ax. So if we act this operator on this function, it must give us a constant and then give back the function. Remember the general formula for eigenfunction equation, a cap acting on phi should give a real number a, then acting on the same phi. So let's try this. So the a cap now is d dx acting on e raised power ax. So if we act d dx on e raised power ax, what is it going to be? So the derivative of e raised power ax is a, this a will come down, a, then this you still repeat the same exponential function, a e raised power ax. Yeah, if you are good at mathematics, then you should know that if we find the derivative of e raised power ax, it will give us this constant coming down, a e raised power ax. So now because we have a constant, and then we have the eigenfunction back. Remember, this is the eigenfunction. We have back the eigenfunction, So surely this is an eigenvalue equation, and we can now say that truly e raised power ax is an eigenfunction of d dx because it gives a constant, then it gives back the eigenfunction. So let's consider another example. Show that sine 2x is an eigenfunction of d squared dx squared. So now remember, the general equation is a cap acting on psi should give us a constant, then gives back the psi. So now the operator here, a cap, is d squared dx squared, and the phi, which is the wave function, is sine 2x. So let's see if we act the operator on the wave function, if we are going to get a constant and get back the wave function. So let's act d squared dx squared on sine 2x. So now this is the second, we are taking second derivative of sine 2x, which means that we will firstly take the first derivative, then take the second derivative. So let's split it. So we can have d dx of sine 2x. What we did is that we just split this second derivative into a derivative of the first derivative. So now what is d ds of sine 2x? The d ds here, d ds that is outside, then d dx of sine 2x will give us 2 cos 2x. Yeah, d ds of sine 2x is 2 cos 2x. So if we have d dx of 2 cos 2x, then let's evaluate d ds of 2 cos 2x. So then we know that this constant will take it outside, then we have 2 d dx of cos 2x. Now what is d dx of cos 2x? That will be minus 2 sine 2x. 2 multiplied by minus 2 sine 2x. That's the d dx of cos 2x is minus. Remember that cos x is equal to d dx of cos x is equal to minus sine x. So whenever you do a derivative of cosine function, it will give you negative of sine function. So d dx of cos 2x, that is minus 2 sine 2x. You bring out these 2, then you put a negative sign, minus 2 sine 2x. So we can say 2 times minus 2, that's minus 4 sine 2x. Now remember that we started with sine 2x, which is our wave function, sine 2x. Now we arrive at minus 4 sine 2x, which means that we got a constant, minus 4, a constant, and then we got back the wave function. We got back the wave function sine 2x, which makes this sine 2x an eigenfunction. because we've said that generally if we get back a constant a and the wave function, then the function is an eigenfunction. Thank you very much. Make sure you like this video, comment and share, and subscribe to our channel. Bye.